Welcome back to GGTutoring. It's Will here, and today we're going to be discussing hydroboration oxidation. So this is basically a two-step reaction involving an alkene that results in the syn addition of an alcohol and a hydrogen. And this hydrogen is added on the more substituted carbon in that double bond, and the alcohol is added to the least substituted carbon in that double bond. And as I said before, it's a syn addition, so they'll both either be wedged or dashed. And then, so now I'm going to kind of go into the electron pushing mechanism of this. So the first thing that happens here is this BH3 molecule will come over in close proximity with this alkene, and the electrons from this pi orbital will come up and attack this empty p orbital on the boron. And simultaneously, these electrons between the boron and the hydrogen will come down and attack the more substituted carbon of that double bond. And that results in this intermediate here. As I said before, this bond right here is forming between this carbon that is the more substituted carbon in the double bond, and this BH2 is also forming a bond with the least substituted carbon in this double bond. This is occurring while these bonds, this pi bond and this sigma bond, are breaking. So you might be asking, why not the hydrogen come down and form a bond with the least substituted carbon of that double bond, and the BH2 to form a bond with this carbon here? And it's actually has something to do with steric repulsion. So these methyl groups and these two hydrogens off this boron will have unfavorable steric reactions, meaning this intermediate over here is going to be a lot more common than this here, just simply due to sterics. So basically the product of this intermediate is this hydrogen coming off the more substituted carbon and this BH2 group coming off the least substituted carbon. And what can happen is more alkenes can come and attack this empty p orbital of this boron and just continuing to add to this boron, which kind of results in this structure here. So this is what we considered the final product of the first reaction, because these alkenes are just going to keep replacing these hydrogens, as they'll take these hydrogens and put them on the more substituted carbon in that double bond. So now I'm going to kind of go into depth about the second step of this electron pushing mechanism of hydroboration oxidation. So this right here is the same molecule as over here. I just replaced two of these alkyl groups with just R, just to make it simpler and I don't have to redraw it every time. So you'll see we have sodium hydroxide and hydrogen peroxide together, and these two are the reactants here, or kind of the first reactants that react with this molecule. So the hydrogen peroxide and sodium hydroxide kind of react and kind of forms this molecule here. And this molecule here, it's very neutrophilic, especially this oxygen here, resulting in this lone pair coming over and attacking, once again, this empty p orbital on this boron. Yeah, so as you see, the reaction between this neutrophilic molecule here and this empty p orbital of the boron form this molecule here. And this is very unstable, as this boron has a negative formal charge. So basically what will happen is it would want to give up one of its sigma bonds here So it will give up one of its R group bonds here. So we'll take this one. So the bonds of this sigma bond here will come down and attack this sigma antibonding orbital of the oxygen-oxygen bond, resulting in the electrons from this to go over here onto that oxygen, will form this molecule over here. So as you see, this bond here broke and this sigma bond here broke. But simply this carbon right here shifted and made a bond with this oxygen here, resulting in this here. So this carbon here is the same as this carbon over here. And basically this step can happen with these other R groups, and it will form just a bigger molecule like this. And I'll draw this out. So the final step, or kind of this is like the final product you end up when reacting with this neutrophilic molecule over here, is this big messy molecule here. So the next thing that happens as to form the final product is, you see we have water over here, so water is going to play a role in separating these alkyl groups from this boron. So these lone pairs on this oxygen are going to come over and once again attack this empty p orbital, this boron, while simultaneously these electrons from one of the boron oxygen bonds are going to come over and steal a hydrogen from that water. And what this will result in is this BOH, and then you have these again coming off the molecule, and then we'll finally have this alcohol on the least substituted carbon of that double bond. So as you imagine, more water can react with these other groups here, and you'll form this over here. So you have this boron that has all these hydroxyl groups attached to it, and then you'll have 3 of these alcohols. As it turns out, using BH3 is not very efficient, as you only get, so say we start with this alkene over here, you only get this alcohol here on the least substituted group about 60% of the time, and the other 40% you get this alcohol on the more substituted group here. And remember, from what I said before, is that this all relates to where the boron will bond to. So in this case, the BH2 group bonded to the least substituted carbon, and in this case, it bonded to the more substituted carbon. And this all has to do with sterics here. So the reason this alcohol here is favored is because there's less steric interaction between these groups compared to like steric interaction between these groups and these hydrogens coming off here. So if you want to make this reaction more efficient and to prevent this intermediate here, what you could do is to make, instead of having hydrogens coming off this boron here, you could have more bulkier molecules. And this results in this alcohol group being on the least substituted carbon over 99% of the time. Meaning the alcohol being on the more substituted carbon of that double bond happens less than 1% of the time. And just to sum it all up, it's just all due to the steric interactions of these bulky alkyl groups. Because if these bulky alkyl groups were where these hydrogens are, this would occur a lot less frequently, just due to increased sterics. Alright, so that kind of sums up the video for today. If you guys have any questions on hydroboration oxidation, just feel free to leave them in the comments. If you guys got any suggestions how to improve our videos, just please leave that down there in the comment section below as well. And yeah, thank you guys for staying tuned, and keep staying tuned for more videos to come.